All right, so prisms are kind of neat. You know, light's passing through, and you see the rainbow of colors there. And it's important to know why that happens. The reason for this is called dispersion, and that's because with different wavelengths of light, they have different refractive indexes. And so, and the dispersion is also called the prism effect. So if we look at this table here, this is a table for different types of glass and quartz. And so what happens is, you know, if let's say you have, let's make it here, we've got air, and then we're going into, let's do silicate flint glass, right? So let's say you have red light coming in, right? At some angle theta. So, you know, when it comes in, and let's look at red here, we can look at the refractive index, and it's about 1.61-ish. So then for glass, its N is 1.61. Air is 1. So it's going to bend, right? And it'll bend a certain amount towards the normal. So we'll have theta 2. Now, what's interesting is, let's go to violet. Let's say we have violet light coming in, and it's coming in like this. Well, it turns out for violet light has a different refractive index, 1.6. Let's see, 1, 2, 3, 4, 5, 6. 1.66 about. So it turns out for glass, it's 1.66. It has a different refractive index. So as it hits, it's going to bend differently. And that's actually what's happening when you have white light coming in. You have white light coming in. It's the whole spectrum, red all the way to red, orange, yellow, green, blue, violet. And their indexes, their theta 2 indexes are going to be different. Therefore, they're going to bend a little bit different. And that's what we get with the prism. They bend slightly differently and spread out. And the more they spread out, you know, the further they get. And we see the prism. This is a good simulation to be able to visualize that. If you just Google search, you know, prism effect, you'll be able to see a visual of that. You know, here's white light coming in. It's going to refract in here, and it's going to refract a little bit differently. And then as it goes from glass into air, it's going to refract again, spreading out even more. What's cool with rainbows is that as sunlight enters in, and if you've ever seen a rainbow, it's because the light is behind you and it hits the rain out in front of you. And the light enters the raindrops, totally internally refracts as well, and it disperses. There's dispersion inside because they're going to refract just a little bit differently. And then after it does that, it's going to refract and totally internally reflect and then head into your eye. And so if you see a rainbow, you know, you'll actually see the full spectrum because the light comes in and refracts a little bit differently. And, you know, in this case right here, you can see how the red light is coming from it, but the violet light and all the rest of the colors would miss your eye going above it. And then down here, violet light will make it into your eye, but the rest of the colors down here will be missed, right? And so you'll see the full spectrum coming into your eye due to all the raindrops in between. So which light has the greatest refractive index? You know, we've got the light coming through, and they all bend a little bit differently, and we can use the chart to do that. Okay, destructive interference happens when you know, you have two waves, same place at the same time, and you know, waves cannot you know, well, the medium can't be in two places at one time, right? So the waves meet, and if we have opposite amplitudes, like we do in this picture, in picture A, you know, we got an amplitude here, and then we have our amplitude here. They mix together. You know, in B, they're starting to overlap, and C, they're overlapped. And we add up the amplitudes. One's a positive, one's a negative, and we end up with an amplitude like this. And then remember, afterwards, they pass through like nothing ever happened. And so, what about a constructive interference? Well, you know, if you have two waves at the same place at the same time and they're in phase, Remember how we did this, right? We drew the third graph, and on that third graph, we could add up our amplitudes, zero displacement, positive amplitude be two amplitudes, neutral, neutral, or node really, of those two there, two troughs, and then so double amplitude trough and so on, right? So the wave would come out something like that. And so, yeah, if we're adding them up in phase, then it's going to end up being double the amplitude at that spot. With destructive interference, if they're 180 degrees out of phase, that means crests are with troughs and troughs are with crests, and nodes are still with nodes, and you end up with, complete destructive interference like nothing's there. And this is a little bit more complex situation, right? If we have two waves, again, the way that we add up our waves is we add up every spot, right? So node as a node, 1 meter, 0.5 meters, 1.5 meters, node, negative 1.5, negative 1.5, so negative 1.5, and so on, right? So, we would have that. On this one, it's a little bit more complex. We have these two waves on top of each other, and they're different kinds of waves now. And you still get the superposition. You still add up each spot. And so if we drew a third graph here, node plus node is node. And then a crest plus, this part would equal somewhere right here. And then a node plus this would just be, somewhere here. And then, trough plus this, we add them up, and it's just slightly above the line. And so, you get a kind of irregular shape there when you add them together. But you add up each spot along the way. What's kind of neat about some of the technology that we use is how light interacts and interacts with other light. And so in a compact disc, what's actually happening is the light comes in, and depending on if the information is a 1 or a 0, the light will hit and then constructively or destructively interfere. So for instance, if we had a pit and we had a land, we would have the laser send out light, and you can see that here, the light sent out here. If it hits a pit, it goes like this. If it hits a land, it goes like this. And then if they're out of phase, that's what's going to hit the sensor, and the light plus light will equal darkness. We'll actually have a crest and a trough for in between crest, in between trough, that'll completely cancel each other out, and we get destructive interference, and that's what would let the player know, okay, this is a 0 or a 1, and then this is binary code. You get a bunch of 1s and 0s, and that's coded to mean some information that you can interpret and then produce music or talking or whatever on a CD. So what I want you to do, if you missed the lesson, I want you to go to Veritasium and then look up interference in water, and then go to 348 and just watch it briefly, and that'll give you a really good visual for what we're about to do. All right, so here's a picture from that visual. We have, a point source here, and the waves are going out from that point source, and you can see those pretty clearly here. And this is a cylindrical wave, right? It's not a spherical wave. This is going out in a cylindrical fashion. So if we were to draw this out, and I want you to do that, go ahead and draw these rings. And these rings, the red lines represent crests. And right in between those, each of those rings you would have a trough. And I want you to draw on the other side another source. So with equal spaced rings. Now, if you notice, once those two start to overlap, there's points at which, at both of these points, right, on the blue ring and on the red ring, both of these are crests. And so if you have a crest plus a crest, you're going to have a huge crest. How about right here? Same thing, right? Right here, same thing. Right here, same thing. Right here, same thing. Right here, right? So at those spots, you're going to have constructive interference with crests. So it will be a double amplitude, right? But if you look at this spot right here, let's say, right here, my circle got a little bit stretched out, but right here, it's a crest plus a trough. So right here you would actually have destructive interference. And then about right here you would have destructive interference. So I drew my rings correctly. So crests with crests and troughs with troughs, and you get that interference there. And you can see that with these two sources. So you can see down here, with this in white, so you can see here's the one source, here's the other source beyond him, and the rings are going out right from them. And what happens is, you know, these spots right here, these are crest plus crest. And then if you look at right here, these are troughs plus troughs. And just like we saw in that last picture. And so this is a really critical idea where you can have waves constructively or destructively interfering with each